Hello everyone, welcome back to the class of differential equations, and we are in the section of 4.2 and 4.3, two sections together, and it is for the second order linear differential equation with constant coefficients, and it must be homogeneous. When we say it's homogeneous, simply means the right hand side is 0. So this time I'm working on example 8 first. And I hope you see this is the second order linear homogeneous and with constant coefficients. Besides, those coefficients are just 1. Those coefficients are just 1. Okay, those coefficients are just 1. And also we did solve the corresponding characteristic polynomial in example 3. So there are two complex roots using the quadratic formula, okay? And then the real part, it is negative 1/2. The imaginary part, as I said several times, we always take out the positive number as the imaginary part. And then according to the arrangement, when we have two complex solutions, two complex roots for the corresponding characteristic polynomial, and we always can have the solution arranged in this fashion, the exponential term times the linear combination of cosine and sine. Specifically, when we plug in negative 1/2 for alpha and the square root 3/2 for beta, this is the solution I'm having here. Okay, the second order linear homogeneous differential equation with constant coefficients and the matching characteristic polynomial. And before I move on to the next example, somewhat I figured out actually the example 9 might better fit what I typed on the notes, okay? Because example 9, it is really closely related. What I want to say here is I hope you can tell for now, a second order homogeneous differential equation, it is solved basically from a quadratic polynomial. It is a characteristic equation. And then what I want to say here is similarly for higher order linear differential equations, they all can be solved from higher degree polynomials. So example 9, this is what I have. It is a third order differential equation. In a long way, we can say it is homogeneous. It is linear, third order with constant coefficients. And then if you remember how to make the arrangement for the quadratic polynomial, okay, you match the order of the degree with the order of the derivative with the degree of the polynomial. So the third order, it is matching the third degree. And then minus y tends to be minus 1. Consider minus y. It is to the order of to the derivative of 0. It's the original function. So it doesn't match the constant here, okay? And then indeed, this is the third degree polynomial. Keep in mind, we do say a quadratic polynomial, there are 2 roots. And then for a third degree polynomial, there are 3 roots. Not just 1. Indeed, there are 3 different roots. Okay. So if you look at the factorization, I'm seeing it can be factored as r minus 1 times r squared plus r plus 1. Okay. Clearly, 1 is a solution. But don't forget, there are 2 other solutions from the quadratic part. This quadratic part, it is solved in example 3 already. Okay, so there are 2 complex roots. And for those 2 complex roots, the real part is negative 1/2, and the imaginary part is this number, square root 3/2. So accordingly, basically, if you remember what we learned in the discussion of matrices, and vector spaces. We say the solution of a third order such a differential equation would form a vector space of dimension 3. So basically, we do expect all the solutions can be written as a linear combination of 3 functions. And indeed, it is just true. We are having a linear combination of 3 functions, because the first one, it is a real root 1, so it is c1 times e to the t. And the 2 other roots, they are complex solutions. So the other linear combination, it is arranged as the exponential function, real part, -1/2, times the linear combination of cosine and sine. This is the imaginary part. Example 9. And also I have one more example for higher order linear differential equation with constant coefficients. And indeed, this is the one from the textbook in section 4.3, example 6. We are having a fourth order differential equation. So accordingly, the characteristic equation is a fourth degree polynomial, r to the 4 minus 16. And then you can give a try to see if you can reach the same conclusion as for factorization. I'm having r minus 2 times r plus 2 times r squared plus 4 equals 0. Hopefully at this moment you see there are 2 real roots, right? 2 and a -2. But did we say a polynomial degree 4 must have 4 roots? So we do have 2 other complex roots from here. 2i and a -2i, 2i and a -2i. And for the complex roots, each has a real part. Hopefully real part, it is a lot easier to identify, or maybe there's no real part. So the real part is 0. And then for the imaginary part, remember, you could take, say, that's 2 or -2, but in general, to find out the solution of differential equation, you only need to take the imaginary part as positive. So accordingly, this time I do expect the solution of this fourth order differential equation is a linear combination of 4 functions. They're all 4 functions, right? And besides, they are linearly independent. Okay, I hope you understand where I get those two exponential functions, e to the 2t and e to the -2t, and how I get those 2 trigonometric functions, cosine 2t, sine 2t. Don't forget, indeed, cosine and sine, they all coming from the arrangement of complex roots. And there is an exponential term with the real part, but e to real part, in this case, e to the 0. So the exponential function for C3, C4 is vanished because the real part is 0, okay? But the cosine, the sine, they both stay according to the imaginary part, beta equals 2. So indeed, the solution of this fourth order linear differential equation, it is the linear combination of 4 linearly independent functions. Thank you for watching.